So let's say that we have a design that we want to run automatically off the onboard clock on the DE0. We have clock circuitry on the DE0, which is described in 4.4 here. So all we have to do is connect the input to our design to G21 or B12. The only issue with that is that this input is 50 megahertz. So often this is much quicker than what a human can see. So we really need a slower clock to work from. So what I'm going to do today is show you how to get a slower clock. How we're going to do it is we're going to actually use that clock to feed a counter. This shows a 4-bit counter. We'll actually use a 26-bit counter because we want to slow it down quite a bit. So if I'm driving a 4-bit counter with a clock, you can see that looking at the least significant bit of this counter, it's half the speed of the original clock. So that's called frequency division. The next bit is f divided by 4, then 8, then 16, and it goes down by powers of 2. So what do we have on the DE0? We have a 50 megahertz clock. If, say, we want about a 1 hertz clock, that means we need to divide by 26. So let's take a look at how we might do that. There's a nice thing in Quartus called the Mega Wizards. And what a Mega Wizard is there's a bunch of pre-installed generic files, and you get to set different parameters on your file. So for example, let's use LPM counter, and we like VHDL, and let's call it my counter. And this is just a little counter that you drive with a clock, and you get to decide how big it is. So if you decide, for example, it's 26 bits wide, then it will go ahead and create a bunch of files, including mycounter_inst.vhd, and mycounter.vhd is always going to be created. So that's in here, and we could go ahead and add it to our projects, and that did two things. One thing is it added the symbol files and whatnot, and the second thing is it added the text files, including the VHDL file. So let's take a look at the VHDL file that was created, and this is one that I made earlier. So this VHDL file simply takes a clock input and generates a 1 hertz output. So it uses a generic LPM counter that is and here's the instantiation of the LPM counter. So it's 26 bits wide, and it's an up counter. So I hook the input of that to the 50 megahertz clock, the output of that to an internal signal called sub-0 here. So there's a signal called sub-wire 0. And then I just pick off the 25th bit of that. So the 26th bit, pardon me, the 26th bit of that, and that's my 1 hertz clock. So you can go through and do the math. It's slightly less than 1 hertz, but it's not bad. It's close enough. So I get 50 megahertz in, I get 1 hertz out. Okay, so that's my clock div thing. This is on the class drive for you just to use. Now let's look at how we might use it. So here I have a design called Blinker, which all it does is flip an LED. So it's got a 50 megahertz input, which is what you have to do because that's going to be hooked up to a pin. And then I have an LED out, and I want the LED to blink at about 1 hertz. So I have a component statement, just like you've seen structural VHDL before. Sorry, there's the component statement. I missed it. So the component for... let me undo that. There we go. I must have deleted the components. So there's my component statement. It's got a 50 megahertz clock in, 1 hertz clock out. So I'll use this in my design. And the way that I'll use it is I'll bring the 50 megahertz clock in, then I'll do a structural statement here, which uses a clock div, feeds the 50 megahertz clock out and the output is called clock. So now that I have a 1 Hertz clock that I can use to do whatever I want to. I can run a finite state machine with it. In this case, I can just run a little toggle with it. So this process changes whenever clock changes, and every time I see a rising edge of clock, it flips the LED. Which is another little thing that you haven't seen yet, is a buffer is simply an output that you can read. So that's kind of a demo. So that shows you how you can use my clock div VHDL, which just pulls in an LPM function, to get a 1 Hertz clock that'll be really helpful for all of your VHDL in your state machines and things like that.